Okay, let's share the screen. All right, so we'll do the best that we can. My streaming has been having some sort of technical difficulties, but we'll do the best that we can. Let me see. Welcome, gentlemen. So, like we are in the home stretch. We are rapidly approaching the end of the term, right? So this week we're working on section 6.4, further topics in algebra, or chapter 6, further topics in algebra, namely 6.4, solving the systems of equations in two variables. But let's do a quick synopsis of like the schedule for the remaining of the semester. So this week we're working on section 6.4, the last of the new material. And then after this week, we're only gonna meet 3 more times, right? So then my thought process is each meeting will just take time to go through an exam, right? So next Monday we'll go through exam 1. That Wednesday is the Wednesday before Thanksgiving, so more than likely we won't meet, right? So you'll be off for the break. So enjoy your break, spend time with your loved ones, do the best you can with the holidays. And I acknowledge that the holidays can be difficult for people. A lot of people have lost like loved ones and this, that, and the other. It can be a challenging time. Then crime goes up. So you want to do your best to just spend time with the people that you care about. Let them, tell them that you love them, stuff like that. And then when we come back from the holiday, we meet on that Monday and Wednesday. That Wednesday, the 30th, should be the last day of class. I'm under the impression that December 1st and 2nd, which is that Thursday and Friday, is the reading period. So you shouldn't be meeting in any of your courses. Okay, so that's not working. Give me just a moment. We can get rid of that. Let's just stop this. Let's try it one more time. Start the broadcast. Because I just noticed in my live stream, it wasn't showing. Let's try this again. But I'm still not seeing it. Usually it's a delay, so I try to. Okay, look like it's working. Okay, 4 p.m. Okay, I think we're golden now. What is it? There we go. Okay. Let me see. Where did I leave off? So, yeah, okay. So, yeah, we have that December 1st and the 2nd is that Thursday and Friday, which is the reading period. And then I think I scheduled for you all's exam to become available that Sunday, December 4th at 11 a.m. And then that following Friday, December 9th at 11:59 p.m. is the hard deadline for everything. So, everything is going to be due. Your final exam is due at that time. So, obviously it's no late penalty because you can't submit the final late. Once the idea is that when you submit your final, you should be done with everything, right? So that Friday, December 9th at 11:59 p.m. is the hard deadline for everything. So my recommendation is to go through Pearson and get as many assignments in order as possible as soon as possible. If you're going back and redoing assignments to improve your grade, again, I would encourage you to prioritize your exams. Those count for nearly 80% of your overall grade. So you want to put those in order first. The thing that you want to prioritize last are the old homework assignments, because that's going to be a lot of work for a little bit of points. The homework is really there to prepare you for the exam. So the main thing are just get your exams in order. So we'll take some time today to go through section 6.4, systems of equations in two variables. And yeah, we're in the home stretch. I don't know that we're going to meet during final exam week. I hadn't decided. Maybe I'll get online during our regular class time, but it's not an official meeting. The last day of class is that Wednesday, November 30th. During finals, I probably will get on during class time just to be available for questions so you guys can find me. You know what I mean? Just making myself available. But once we meet on the 30th, you submit your final, and then that's it. You don't really have to meet after the 30th. Okay. All right. So today, let's see. Okay. So today, let's take some time to go through, get as far in chapter 6 on section 6.4 as we can. Whatever we don't do together, keep in mind I do have a recorded version of this, a pre-recorded lecture that goes through this entire section. So we just take some time to do what we can together. I just try to make myself available for questions, things of that nature. But you always have those pre-recorded lectures in case, for whatever reason, this stuff goes sideways, all right? Technology is temperamental, so that's why I did it that way. So in section 6.4, systems of equations in two variables, we have a few objectives. One, we like to verify a solution to a system of equations. Two, we like to solve a system of equations by the graphical method. Three, we like to solve a system of equations by the substitution method. Four, we like to solve a system of equations by the elimination method. And five, we like to solve applied problems by solving systems of equations, okay? So we have some definitions. A set of equations with common variables is called a system of equations. If each equation is linear, then it is a system of linear equations or a linear system of equations. If at least one equation is nonlinear, then it is called a nonlinear system of equations. Here's a system of two linear equations and two variables, right? So, when we have a system of equations, every time we have an unknown, we need an equation. Notice that here we have two unknowns, namely x and y. So we need two equations in order to solve the system. That's why we have two equations, okay? So then a few more definitions. A system of equations is sometimes referred to as a set of simultaneous equations. A solution of a system of equations in two variables x and y is an ordered pair of numbers a and b, such that when x is replaced by a and y is replaced by b, all resulting equations in the system are true. The solution set of a system of equations is a set of all solutions of the system, right? So a solution to a system of equations, it's gonna show up in a few ways. One way that it shows up is you have an ordered pair, right? Some x comma y. When you plug in that x and that y into any equation and it makes it true, then that's how we verify that a solution is a solution of a system, right? So here we're asked to verify that the order pair 3, 1 is a solution of the system that we see given, okay? So let's see. So it's basically saying when we replace x with 3 and y with 1, it should make both of these guys true. So if we say 2 times 3 minus 1, that's going to be 6 minus 1, which is 5. Okay, so that checks out. Okay. And then if we say 3 plus 2 times 1, that's 3 plus 2, which is also 5. So that checks out as well. Okay. So because when we plug in the order pair 3, 1 into both equations and it makes them both true, then the order pair 3, 1 is a solution of this system. And here's a type version of what we just experienced. Okay, here we're asked to use the graphical method to solve the system. So we're going to need some graph paper. Graph paper. Okay, I think this is about enough like that. Okay. So let's start with the origin about here, okay? And anybody have a favorite color? You guys have a favorite color?
Orange.
Orange. Is there anybody else got a favorite color? Any other favorite colors? Mr. Stooks, I just realized you're back. Hey. I was like, hey, we went through all that to get you back into class, and then you disappeared. I was like, wait a minute, what's going on? But yeah, it's all good. All right. So I know there was one for orange. I think a student earlier said purple. So we'll do the first equation in orange. Now, so we're going to graph these two equations. So notice that the highest exponent on any variable is a 1. So both of these are graphs, both of these are lines. So what we're going to do is solve for y in each equation and then graph that, right? So in the first one, we're going to get y equals 2x minus 4, okay? And I'm going to use purple. The second one, we get y equals If we subtract the 2x, it's going to be a negative 2/3 x plus 4, okay? So equation 1, we're going to do it in orange. Equation 2, we're going to do it in purple. Let me see. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4, 5. That should be enough. 1, 2 should be enough, right? We're going to let this be our positive x direction. Nope, let's try it again. Okay, that'll be a positive x. Why is it doing that? Under. Like this. This will be our positive x here, and this will be our positive y. Okay, here's the origin. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2. These are negative. Okay. So with the orange one, the y-intercept is -4, and the slope is +2. So if we go up 2 and over 1, up 2 over 1, up 2 over 1, yada, yada, yada. Connected with the straight edge. Okay, so that's the graph of the orange. And then the purple with equation 2, the y-intercept is 4. The slope is a -2/3, so down 2 and over 3 is here. Down 2 and over 3 is here. Here, and then connected with the straight edge. Okay. We get something like that. Okay. So notice that these two cross at the ordered pair 3, 2. Our claim is that the ordered pair 3, 2 is a solution to the system. That's fine for now. Let me go style. No. Paper like this. Okay. So then it is a good idea to confirm that the order pair 3, 2 works in the original system, right? So when x is 3, y is 2, it should make both equations true. Okay. So then 2 times 3 minus 2 is 6 minus 2, which is 4. That one checks out. Okay. And then 2 times 3 plus 3 times 2 is 6 plus 6, which is 12. And that one checks out as well. Okay. Okay, we're looking good. Let's keep going. What's the time? I think we got everybody, so that's cool. And here's a typed version of what we just experienced, right? Okay. Okay. So then when we're working solutions of systems of equations, the solution set of a system of 2 linear equations and 2 variables can be classified in one of the following ways. We might have one solution like what we just experienced. We say that this system is consistent and the equations are said to be independent. All right, so when we have one solution or a finite number of solutions, the system is consistent and the equations are said to be independent. We could also have where there's no solution. There's no solution. The lines are going to be parallel, and we say that the system is inconsistent. All right, so we're working with parallel lines. 2 lines with the same slope and different y-intercepts are inconsistent. And then the third way solutions could appear could be, we could have infinitely many solutions. So then that's where one line is going to be on top of the other. The system is said to be consistent, and the equations are said to be dependent. Algebraically, it usually appears as one equation is a multiple of the other. Okay. My dog is in there losing her mind for some reason. Okay, we're asked to solve the system. Okay, and so now we want to introduce the substitution method, right? So with the substitution method for solving a system of equations, you solve for one variable, and then you take that solution and plug it into the other equation, right? So if we're going to solve for y, it looks like equation 2 is easier to solve for y in. So if we solve for y from equation 2, we get y equals 2x plus 9. Then we can take this and plug it into equation 1. So we'll have 2x minus 5 times y equals 3, but we plug in that y we just found of 2x plus 9. So now we have one equation, one unknown we can solve. So let's distribute this. All right. We get 2x minus 10x. What is that? Minus 45 equals 3. You get negative 8x equals 48. X equals negative 6. Okay. So we solved and we got that x equals negative 6. So then we can take this and plug it back in to solve for y. So we're just plugging it over here. So then y is going to be, it's going to be negative 12 plus 9, which is negative 3. Okay. So then our claim is that the solution to the system is going to be the ordered pair negative 6 comma negative 3. Okay. Okay. Let's keep going. All right. And it is a good idea to plug it in to check, but I'm just gonna rely on my prepared notes. So we got negative 6 and 3. So when x is negative 6, y is negative 3, right? Okay. So let's give this one a go. So we can still use the substitution method, right? So just to be, well, okay, if we solve from y, it looks like it's easiest to solve for y from example 1. So if we solve for y from example 1, from equation 1, we're going to get y equals 3 minus x, okay? Then if we take this and plug it into equation 2, 2x plus 2y equals 9, but y is going to be 3 minus x. So then now we have one equation, one unknown, so we can solve, okay? So then we're going to get 2x plus 6 minus 2x. Yeah, minus 2x equals 9. A number plus its opposite adds to 0. If we subtract 6 on both sides, we get 0 equals 3, which is what? False. This is false. So when you're solving a system of equations and all of your variables cancel out, all the variables are gone, and you finish with a false statement, that means the system is inconsistent. These are parallel lines with different y-intercepts. So then this is going to be no solution. Okay. And then here's a type version of what we just experienced, right? I think they did the same thing. Okay. Okay, that's good. Let's give this one a go. Let's use the same technique, right? Substitution where we solve for one equation, solve for one variable. It looks like solving for y in equation 2 might be the most simple. So if we solve for y from equation 2, we're going to get 6 minus 2x. And then we take this and plug it in equation 1. 2 times y equals 12, but our y was 6 minus 2x. So then we can distribute. We get 4x plus 12 minus 4x equals 12. Ultimately, if you combine like terms and subtract 12 from both sides, you'll finish with 0 equals 0, which is true. So when all of your variables cancel and you finish with a true statement, that means the system is consistent and the equations are dependent. In other words, one equation is a multiple of the other. Notice if we multiply equation 2 by negative 2, we'll get equation 1, all right? So then that means that we have infinitely many solutions, and all solutions are going to take on the form, no matter what x we choose, our y is going to take on the form 6 minus 2x. So you could even choose your favorite x value right now, find the corresponding y, and then that ordered pair is going to work. Okay, it's going to work in the system, right? So for instance, like if we let x be 1, if x is 1, then y is going to be 4. So then the ordered pair 1 comma 4 is going to work in both of these equations. So 4 times 2 is 8, plus 4 is 12. Negative 2 minus 4 is negative 6, right? You can choose another x value. You can let x be 0, then y is going to be 6, all right? That'll work as well. So when you have dependent equations, basically one equation is a multiple of the other, you're going to get infinitely many solutions that's going to take on a form similar to this. Okay. Okay. All right, so let's do a demo on the elimination method. So we saw a demo. Let me see. Do I need some space? I think I do, but I might try to get it if it. We saw a demonstration using the substitution method where we solve for one variable from one equation and then take that outcome and plug it into the other equation. So now here we're going to multiply each equation by some number. The goal is to whichever variable we want to eliminate, we want it so that the coefficients in both equations have the same number for that variable, but they have opposite signs, right? So for instance, like if I wanted to eliminate the x, I could multiply the top row by 3, so we would distribute a positive 3, and I could multiply the bottom row by negative 2. Thank you. Bottom row by negative 2. Okay. So then when we do this, on top, we're going to get 6x plus 9y equals 63. And then on bottom, we're going to get a negative 6x plus 8y equals negative 46. Okay. So now we can add the two equations together, and the like terms are going to add to 0. Number plus its opposite adds to 0. We get 17y equals, let's see, that'll be 13. So 17, divide both by 17, and y equals 1. Okay. So then we can take this and plug it into either equation to solve for x. I feel like for equation 1 might be a little bit easier. So when y is 1, 21 minus 3 is what, 18? So then x is 9. I just didn't write it out because I ran out of space. Right? But I plugged in y equals 1 into equation 1. So then the claim is that the ordered pair 9, 1 is the solution to the system. All right, so that was a demo on the elimination method. All right, and I think I'm just going to piggyback on my prepared notes. You see the 9 there and the 1 there. So then the solution set is 9, 1. Again, you would just plug in when x is 9 and y is 1, and it should make both equations true. Okay. So then with this one, we're going to go back to using the substitution method, but it's an augmentation to it called the linearizing substitution. So something like this, we want to change the formula to something that's easier for us to work with. So what we're going to do is let u be 1 over x and let v be 1 over y. So we're going to replace the 1 over x's with u, the 1 over y's with v. So then our system of equations becomes 2u plus 5v equals negative 5, okay? Then we have 3u minus 2v equals negative 17. Now we're back to a system of linear equations like we had before. I think I'm going to cancel. I feel like canceling the u might be a little bit easier. So if I'm gonna eliminate the u, then I'm gonna multiply the first equation by what, 3, and distribute that 3 across the entire row. And then I'm gonna multiply the second equation by negative 2. The goal is so that the coefficient of u, they're both going to be 6 in this case. It's the least common multiple, but we want them to have opposite signs, okay? So then this gives us 6u plus 15v equals negative 15, negative 6u plus 4v equals 34. So then when we add these equations together, a number plus its opposite adds to 0. So we've successfully eliminated u. We get 19v equals 14 plus 5 is 19. So then v equals 1. Okay. So we solve for v. So now let's go back and solve for u. I'm just going to continue working over here. Let's see, if v is 1, I'm going to use equation 2. So then we have 3u minus 2 equals a negative 17. So then 3u equals negative 15. So then u equals negative 5. Okay. So then we need to substitute back. So earlier we said that 1 over x equals u. So that means 1 over x equals negative 5. Cross multiply, x equals a negative 1 over 5. Kind of running out of space. And then 1 over y equals v. 1 over y equals 1. So then y equals 1. Okay. So then our claim that the solution to the original equation is going to be negative 1 by 5, comma 1. So our claim is that this ordered pair should work. Okay. And if you plug it in, I mean, we can do it quickly. Let's just go ahead and check it. All right. So if x is a negative 1 by 5, let me see. That's going to be what? Negative 10 plus 5 is what? Negative 5. That one checks out. Negative 15 minus 2 is negative 17. That one checks out as well. Okay. All right, guys. I actually have an appointment I need to get to. I think we're good, right? I'm just looking for something like right here. Did you guys want to ask me any questions? Do you have any questions for me? Come on. There we go. Okay, let me make a copy of what you saw me writing available. Send the box. Okay. When this bar finishes loading, you'll receive a copy of anything that you saw me writing. And if there aren't any burning questions, we're actually going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. I'll see you on Wednesday, same time, same place. Take care, guys. Peace.